Welcome back to the workshop. We want to continue taking a look at section 3.6, marginal distributions. And in this video, we want to consider two continuous random variables. So when it comes to continuous random variables, we don't have that same sort of table that we were looking at. But what we do have is we have the idea of the visualization. So if we go to the next page here, this is the graph of the function for the example we want to consider. Now I can't rotate this or move this or really do much of anything with this, but what I want to say is when we consider a marginal distribution, we're still taking a look at essentially the sides of things. So we just take a look at a perspective from the side. So if I want to consider, for example, the probability that, let's see here, this variable is x, this is z, or the function value, and then this is y. So if I want to take a look at the marginal distribution of x, what I'm doing is I'm essentially just looking at it from this perspective, okay, from down here. So if I want to find the probability that x is between, say, let's see here, this is 1 and let's see, 1, 2, 3, so it's somewhere around here and here, something like that. Then I'd be looking at all of this, all of the area underneath this portion. Oh, I want to leave that there. All the volume underneath this surface. Okay, so I'd be looking at that, and I'd just be finding the volume here. Okay, underneath this portion. It goes on forever this way, and it goes on forever that way, because I'm ignoring what happens in y. I want to consider all possibilities of y as I consider this specific range in x. And that's exactly what we were doing here as well. I'm looking over all, let's see here, these are the x values, these are the y values. So I'm looking over all possible y values, and that gives me the probability for one particular x value. I look over all the y values, and that gives me one particular probability for one particular x value. And that's essentially exactly what we want to do here. I don't want to consider a specific set of y values. I want to consider all of them. So I integrate over all possible y values to get rid of the y's, right? That gets rid of the y, and then I can just integrate over the appropriate portion with respect to x. And that's exactly what we've got going on in our definition here for our marginal densities of a joint probability density function. So if x and y are continuous random variables, and this is a joint probability density function, then we can consider the marginal distribution, or sorry, the marginal density of x as g of x is equal to the integral from negative infinity to infinity. Of course, essentially we would only integrate over the non-zero regions, because integrating over the zero regions contributes 0. So integrate from negative infinity to infinity of f of x comma y, and we want to consider all possible y values, so we're integrating over y here, and then we can think about what the density, the probability density is for x, and that's exactly what this results in, is just a probability density for x, and of course the x values can range from negative infinity to positive infinity, or wherever they're non-zero, you might think that as well. So that's marginal density of x, and h of y would be the marginal density of y. And of course, in this case, we want to consider the probabilities for the random variable y, in which case we have to get rid of or look at all possible values of the random variable x. So we again integrate f of x comma y, the joint density, and we integrate with respect to x. That gets rid of the variable x from the function, and it's only in terms of y, and we can use that as the density function for y, the probability density. And of course, we can plug any value we want into that function as well. It might be 0 for most of it. All right, so here is a joint probability density. We want to find the marginal density of X. Okay, just X in this case. That keeps things a little bit easier. But if we want to find the marginal density of X, right, that's this function is exactly this one here, and we want to consider being able to find those probabilities. Function that's going to be the density for X. So we integrate over all possible Y values, and then we say, all right, well then G is just right. We integrate as we need to find the probabilities for X. So G of X, the marginal density of X, is the integral from negative infinity to positive infinity of f of X comma Y dy. But in this case, right, we have that we're only considering Y values greater than 0. So this is the integral from 0 to infinity. Well, we are considering others as well, but it's 0, so we can just essentially ignore it. Since we're looking at only where the function is actually defined, we are integrating for x, y, e to the negative x squared plus y squared dy. All right, now from here, of course, you might want to make a substitution. You might, probably a substitution might be the easiest way to go. If you let u be negative x squared plus y squared, then essentially you'd be able to end up with the integral of e to the u, or some constant multiple of e to the u. But when you do that, you would find, of course, we need to use limits because it's an improper integral. So the limit as a goes to infinity of, when we integrate this, we get negative 2x e to the negative x squared plus y squared. And we're evaluating that from 0 to a. And this is going to give us, when we evaluate at a, it is the limit as a goes to infinity of negative 2x e to the negative x squared plus a squared. Let's see. Yep. And then minus negative 2x e to the negative, evaluate at 0, x squared plus 0. There we are. Of course, negative negative gives us a positive. And as we let a go to positive infinity, x squared, whatever it is a positive number. So positive plus a number going to infinity is going to be a number that goes to infinity. Add a negative sign on there, and e to the negative infinity approaches, or as this approaches negative infinity, the overall expression here is going to approach 0. So this goes to 0, and all you're left with is 2x e to the negative x squared. So I said here that g of x is equal to that, but we should recognize that it's also defined for x values. It's defined differently for x values that are less than or equal to 0. So g of x is equal to 2x e to the negative x squared for x greater than 0 and 0 otherwise. Of course, the integral of 0 is 0, which is what gives us this part. All right, and that's it. It might be worth, again, just maybe considering considering Mathematica. And I didn't open up a new one for us, so let me open up Mathematica and see if I can recall the function that I need to plot, or the command that I need to plot. Let's see here. I believe it's plot 3D. Excellent. So go with a new document, and I want to do a plot 3D, 3 is good, capital D, there we go, square bracket. And the function that we're looking at in this case is, we said 4 times x times y times, now this is a little bit different. I don't do e to something, I do exp, which is the natural exponential function, and we're raising that to the negative of, all right, e to the negative x squared plus y squared. Close that parenthesis, close the exponent. That's the function we want to graph, and we want to graph it with x values. I did from 0 to 10. 0 to 10, there we go. And then the other variable in this case is y. From 0 to 10 is also what I did there. Close it up. Let's see here. I must have done something wrong because that looks a bit different than what we had in our notes. But it's awfully interesting looking. All right. Very interesting looking. Huh. Let's see, x, 4xy. See if I can figure out what I did funny here a moment. I'm actually going to pause the recording for just a second. All right, so rather than waste your time trying to get this all typed in with you listening to me, I realized that I used a slightly different function for our lecture notes. So I did a region plot instead of just a plot. So plot 3D versus region plot 3D. And it works a little bit differently. You have to give conditions because you're plotting a region, not a function, not a graph. So what we do here is we say we want all of the z values that are less than this particular equation, which is the equation of interest. So that's actually filling in the area below. And then I want to consider x from 0 to 10, y from 0 to 10, and z from 0 to 1. So that way it's going to kind of cut everything off at 0 as well. So when I do that, hopefully it gives us what we're looking for. And yes, it does. This looks a little bit more similar to what we had in our notes. But what I wanted to do this for, and actually here we can improve this. This looks kind of boxy, and we can improve that by saying plot points and then a dash like that. That's going to give us an arrow, and let's try 50 points instead. And there we go. That looks a bit smoother. So then I can turn this, and what I'm doing is I'm essentially making it so that way I've got, right, when I look at this now, I'm looking at essentially the distribution of x. Okay. Now there's some depth here too, so that makes a little bit of difference of what's going on. But essentially what I'm doing is I'm taking taking this perspective, and if I wanted to do, if I wanted to look at what it is for y, I would just turn it a little bit. It's kind of difficult to figure out here. See if I can get this turned and make it a little bit bigger. There we go. So now I'm essentially looking at what the distribution of y is. So you can look at the distribution of y, you can look at the distribution of x, and these are the marginal distributions. Now this doesn't account for, again, the depth that you have here, but it's essentially what's going on. All right. So hopefully that provides a little bit of insight as to what it means to look at the marginal distribution for a continuous random variable. So we'll continue on looking at this section for 3 or more random variables with a couple of more videos. So I'll see you guys back in the workshop very soon.